Hello dear students, welcome you all. In this lecture, I am going to take up the next question from section B of this question paper. And the question is question number 2. In the earlier lecture, I have solved question number 3. Right. So in today's lecture, I am going to solve question number 2. So question number 2 have two parts, part A and part B. In part A, the examiner is asking you regarding the solution of a differential equation. Right. You can see here the differential equation is written here, and in B part, so that the expression for fictitious force in rotating frame is given as, this is the article. So first of all, I am taking the differential equation, right? The differential equation is d square by upon dx square plus 2 d by upon dx plus 2 by is equal to 0. This is the answer to section A, right, of question number 2. Right. Now you look at this equation. First of all, we have to identify that which type of differential equation this is. Like this is equation number 1. So from the knowledge of differential equation, we have gone through in details regarding the differential equations in the 12th class also. This is a second order linear homogeneous differential equation with constant coefficient, right? Linear homogeneous equation, right, with the constant coefficient. You can see coefficients are a constant, right? You can say 1 here. So this is a second order linear homogeneous differential equation, and we know how to solve this type of differential equations. To get the solution of this differential equation, we start with assuming let y is equal to e raised to power alpha x is the solution of equation number 1, right? Now we'll find out the exact value of alpha. Then by putting it here, we can write down the solution, right? So let this is equation number 2. So after taking the derivative of equation number 2 with respect to x, I got dy upon dx is equal to alpha into e raised to power alpha x. If I take d square y upon dx square, means ddx of this equation, then it will simply alpha square e raised to power alpha x. We know very well what is the rule of differentiation. Now I'm going to put the value of this dy upon dx here, right, and d square y upon dx square also here, right. So then also the value of y will be put. So when I put all these values here, what I got? I got alpha uh, square e raised to power alpha x plus 2 alpha e raised to power alpha x plus 2 into by e raised to power alpha x is equal to 0, right? E raised to power alpha x is common, so I am left with the alpha square plus 2 alpha plus 2 into e raised to power alpha x is equal to 0. So as e raised to power alpha x cannot be equal to 0, because in that case we will get only 0, y is equal to 0 solution. So this is not possible. So it means alpha square plus 2 alpha plus 2 is equal to 0. So when I simplify, it is simply a quadratic equation in alpha. So we know very well the solution alpha is equal to minus b plus minus under root d. D is what? B square minus 4 into a into c means 2 divided by 2a. 2a means 1, right? So when you will simplify it, 4 minus 8, right? 4 minus 8, you got 4. So but the 4 will be of negative, minus 2 plus minus under root minus 4 we have divided by 2. So minus 4 under root means it is now minus 2 plus minus 2 iota, right, divided by 2. So when I took 2 common, it got cancelled. So I got minus 1 plus minus iota or 1 iota. So I can write it in the form of P plus iota Q, right? Here P is equal to minus 1 and Q is equal to 1, right, in this equation. So you can see here. So now when I took in this way, that is the first case, then that I took minus 1 plus iota. In that case, P is equal to 1, Q is equal P is equal to, sorry, minus 1, Q is equal to minus 1. So in that case, the general solution y is equal to, now putting it here, putting this value here, this equation number 2, e raised to power alpha. Alpha means P plus iota Q x, right? So when you will expand it, it will become e raised to power P x plus iota Q x. So it becomes, when you expand it, a cos of P, sorry, a cos of Q x plus b sine of Q x into e raised to power P x, right? Because you can write it in this way, e raised to power P x into e raised to power iota Q x. So you can expand e raised to power iota k x. E raised to power iota theta is equal to cos theta plus sine theta, right? A and V are constants. So now you can put the value of Q. So Q is 1, so it becomes A cos of x plus B sine of x power into e power, P means minus 1. So it is a minus x. So this is the solution of this differential equation. Similarly, you can take P is equal to minus 1 and Q is equal to minus 1, because that will be the other case. So in that case, what you will get, y is equal to a cos of, in that case it will become minus, now Q is also minus 1. So Q into cos of minus x plus b sine of minus x into e raised to power minus x. In that case, this is the solution. Now we can go to, it will become cos minus theta, cos theta. So it becomes a cos of x, b sine minus theta minus sine theta, minus b sine of x into e raised to power minus x. So this is y2, right? This was y1. So this is the second solution, right? So this is the way of solving this type of a differential equation. So how we solved it? First of all, we identified this equation, that it is a linear homogeneous equation with constant coefficients, and this is the way of solving these equations, and then finally we arrive at the results, right? So this is the answer to this question, right? Now I am going to the next part of this question section, option part number B, right? So now I am coming to the part B of question number 2, and the part B is, show that the expression for fictitious force Fr in the rotating frame is given by this expression. So this is the question that deals with the fictitious force acting on a body when it is present in a non-inertial frame of reference that is having rotational motion. Now I have explained in the earlier lectures that what is the difference between inertial and non-inertial frames. Inertial frames, once again I want to repeat, inertial frames are those frames which are either at rest or moving with uniform velocity, and the law of inertia holds good. But non-inertial frame of references are those frame of references which have acceleration. It can be translational acceleration or it can be rotational acceleration. So here in this lecture we are considering the case of rotational acceleration. We have a frame that is having rotational motion. So we will see how the fictitious or pseudo forces arise in that frame on a body, right? So for it, let's consider first of all two coordinate systems that are given here, or two frames. This is the frame S that is shown in the blue color. This is frame S, and this frame of reference is represented as S, and it is fixed in space. It is not moving. What the second frame that is shown by the red color, this is x dash axis, y dash axis, z dash axis. It is the rotating frame of reference. This frame of reference is rotating with angular velocity vega, right, in space, right? But for convenience, we consider that the origin of these two frames coincide, and it is here, that O dash is equal to O. The origin of both frames coincide, but the only difference is that this frame, the second frame S dash, is rotating about the Z axis in this way, right, with angular velocity vega. But the first frame, that is X, Y, Z, represented in blue color, it is fixed. Now suppose we have two frame of references, two observers. One is in inertial frame S and other is in non-inertial frame S dash. Suppose a body is present in space at point P that has coordinates x by z according to the first observer, and coordinates x dash, y dash, and z dash according to the second observer. Two observers are doing the observations. According to first one, because the origin of the both frame coincide, according to first observer, the position coordinates are x, y, z, x, y, z, and according to second, x dash, y dash, z dash, right? I have also shown the unit vectors. Unit vectors in the first frame are I, j, k, whereas in the second frame, I dash, j dash, and k dash, because the direction is different. And the another thing about these unit vectors, in the first frame, that is S frame, these unit vectors are fixed in space, I, j, and k, because the frame is at rest. It is not rotating. So these unit vectors are not changing with time. They are fixed. But these unit vectors, that I dash, j dash, and k dash, they are continuously changing. Why? Because the directions are changing with the rotation. As the frame is rotating, so these vectors, unit vectors, are also changing. So while taking the differentiation, we have to keep in mind that I, j, k are constant vectors, whereas I dash, j dash, k dash are variables, right? Now, let R is the position vector from origin to here, right? Now we know very well, according to two observers, I can write the expression for R and R. It will be xi plus by j plus zk for the first observer, and R, it will be x I dash x dash, sorry, I dash plus y dash, j dash, plus z dash, k dash. This is the value of this vector, right? R, this vector that is connecting this point to this point, because the vector is same between these 2 points, but the coordinates are different. X, y, z, x dash, y dash, z dash, I, j, k, and I dash, j dash, k dash. Now I am taking the let this is equation number. Both these are represented as equation number 1. Now let's take the differentiation of this one, that is dr upon dt. Now dr upon dt, we know very well it will be representing the velocity. Let's take differentiation of this one. Sorry, second one, right? What it will become? D dt of x dash I dash plus y dash j dash plus z dash k dash, right? I took this one, right? Then what it will become in the next step? Now as both I dash and x dash, they are variable, I told you, so we will have to apply the product rule of differentiation. Dr upon dt will be equal to d x dash upon dt I dash, right, plus d I dash upon dt into x dash. This is the differentiation according to product rule. Similarly, dy dash upon dt into j dash plus dj dash upon dt into y dash plus dz dash upon dt into k dash, right, plus d k dash upon dt into z dash. So this is the differentiation of all these three terms. So then after arranging the like terms, I got d x dash upon dt into unit vector I dash plus d y dash upon dt into unit vector z dash plus d z dash upon dt into unit vector k dash. I considers dx dash, dy dash, dz. Other three terms that will be left, they are x dash d I dash upon dt plus y dash d z dash upon dt plus z dash d k dash upon dt. Now I have these two. Now what is this? You look at this. What is this? This is obviously the velocity according to the second observer. Dx dash upon dt I dash plus dy dash upon dt z dash plus dz dash upon dt k dash. So we can say that this is the velocity of this body that is moving in space, and at this particular time it is at point P with respect to the rotating observer, right? Whereas we can say that this is the velocity with respect to the fixed observer, right? So in that case, dr upon dt, I can write it is fixed observer, that is equal to dr upon dt, it is rotating observer, plus x dash di dash upon dt plus y dash d z dash upon dt plus z dash d k dash upon dt. So this is the expression that I got from here. I simply replaced this as the velocity in the rotating frame. So when I took it as the velocity in the rotating frame, then I have to take this as the velocity in the stationary or fixed frame, right? Now I have to simplify this term, right? We know very well that what is the relation between the velocity and angular velocity. V is equal to vega cross r. We have learned about it. So I can write V means dr upon dt, right? That is equal to vega cross r, right? So if I put in place of r, I put I dash, right? Because this is a vector. So in place of r, if I put d I dash, I simply replaces r with I dash upon dt. So in that case, it will become vega cross I dash vector. Sim, right? So this is the first one. Similarly, I can do it for others. I can get d z dash upon dt is equal to vega cross j dash, right? Similarly, d k dash upon dt is equal to vega cross k dash vector, unit vector. So I got 1, 2 and 3. These three terms I am going to put here, right, in this equation. So what I will get when I will put it here, I will get is equal to dr upon dt rotating plus bracket x dash into vega cross I dash plus y dash into vega cross j dash plus z dash into vega cross k dash. This is what I got from here. So now I can write it in this way also further. dr upon dt rotating plus I took vega outside cross I multiplied x dash I dash plus by dash by dash j dash plus z dash k dash. This is the thing that I got here. Now, what is x dash I dash plus by dash j dash? What is it? It is basically the now position vector with respect to the rotating observer I have written here, right? So I can replace it with r, but we have to remember that this is the position vector with respect to the rotating observer, right? So in the next step, I can write plus vega cross r, right? But this, right? And this term will be as it is. So this is what I got here. So now I have to add page here. So now I'm going to the next step. I can write this equation here, dr upon dt. I'm writing the complete equation for convenience. Fixed, that is equal to now dr upon dt rotating plus vega cross r. But this position vector is with respect to the rotating observer, right? So we can say B fixed is equal to B rotating plus vega cross r, right? Because this is the velocity with respect to the fixed observer, rotating observer, and this is angular velocity, and this is the position vector with respect to the rotating observer, right? Now I'm going to take the velocity with respect to the rotating observer. B rotating, that is equal to dr upon dt with respect to rotating observer, right? And similarly this one, B fixed is equal to dr upon dt fixed. This is the position vector that I take it here. So now in this equation, in only operator form, let this is equation number 3. Here dr upon dt and r. If I only consider the operators, right, means ddt and vega, then I will get what? I will get ddt of a physical quantity fixed, that should be equal to ddt of a physical quantity rotating plus vega cross that physical quantity will come here. So this relation will be valid for any physical quantity, right? It will be true for all vectors, right? We can replace any vector in place of r here, right? So if we put here bf, right, in this equation, then this obviously this should be valid if it is valid for all vector, this equation number 3. So now I am, let this is equation number 4. I am putting here bf vector, bf, right? So what I will get? You will get d bf upon dt fixed is equal to d b fixed upon dt rotating, right, plus vega cross bf. This is what I got from modifying this equation number 4, and this is equation number 5, right? So in the next step, what I'm going to do, I'm going to put the value of bf, right, bf in right hand side only, because right hand side deals with the rotating frame and this deals with the fixed frame. So I have to replace bf with the br and this. factor. So if I put this value here in the right hand side, then what I will get? I will get this is equal to d dt of Bf means Br plus vega cross R. Rotating, right? Now it is, there is no need to write rotating because we have replaced it, plus vega cross Br plus vega cross R, right? So when you will take the differentiation, this will become d upon dt B rotating frame plus d dt of vega cross R plus vega cross Vr in here plus vega cross R. This is the term that I got here. Now expanding it, d Vr upon dt plus d vega upon dt cross R plus vega cross dr upon dt. I applied the product rule of differentiation for the vectors, plus vega cross Vr plus vega cross R, right? So now here I got d vega upon dt. Now this is dbf upon dt final fixed, sorry, d velocity fixed upon dt fixed. So I can say that this is the acceleration with respect to the fixed frame, right? This is then becomes acceleration with respect to the rotating frame, plus now d vega upon dt. Let vega is a constant, the angular velocity is a uniform constant. So in that case, if vega is constant, then d vega upon dt will be 0, then this term will become a 0 in case of vega constant or uniform. This is equal to 0, right? So I'm left with the plus vega cross, what is dr upon dt? It is Vr rotating, because in this side we are dr upon dt means velocity with respect to the rotating frame, because in the right hand side we are taking the rotating frame terms, plus vega cross Br plus vega cross R. Now it is obviously going to become 2, they are going to add up. So what I got, A F is equal to A rotating plus 2 vega cross Br, right, plus vega cross R, this one. I can write it as A rotating is equal to A fixed minus 2 vega cross Vr, right, minus vega cross R, right. Now this is the expression for acceleration in rotating frame, and it is written in terms of the acceleration in fixed frame and other terms. If m is the mass of the particle that we are talking about, that is moving in space, then let multiply this equation with m on both the sides. Here it is m, here it is m, right? So what I will get? I will get, now this is what? Force acting on the body in a rotating frame. This is the force acting on the body in a fixed frame, right, or stationary frame, minus 2m into vega cross Br minus m vega cross R, right? So this is the expression that I got when I multiplied it by m, and now this expression is representing actually the force. So you can see here that the force acting on the body in the rotating frame is different from the force acting on the body in a fixed frame. We have two terms here. This is the first term and this is the second term. Minus 2m vega cross Vr and minus m vega cross R, right? So these two terms are actually the fictitious forces that arise in the rotating frame of reference, and these fictitious forces arise because of the acceleration of the frame of reference. This term arises when the body is moving in the rotating frame, and this term is arising when the body is present at rest in the frame. Even then this force is acting on the body. So these two forces are the fictitious forces. This force is known as the Coriolis force, right? Coriolis force, and this is known as a centrifugal force. So we can say that two different forces, one is centrifugal force and one is a Coriolis force. These forces are acting in addition to the actual force in the rotating frame of reference. I am separating these two forces here. These are now, even we can write it as F rotating is equal to F fixed plus F Coriolis plus F centrifugal, right? So this is the expression that we have derived, that was asked in the examination. I'm taking back you to that previous page. You can see here this was the expression: F rotating is equal to F stationary minus m vega cross R minus 2m vega cross Vr. So you can see here we have done the same thing. F is equal to this, right? F stationary minus m vega cross R minus I, right? So this is the answer to this question. Even the examiner can ask you about the nature of these forces, that this is the Coriolis and this is the centrifugal force, right? So this is all about this question, right, that was asked here. So now section B is complete. Both the questions has been attempted in this, solved in this lecture. So in the next lecture I will take up another questions from the question papers, right? So thank you very much.